late. This room is double booked. Can you still hear me? Is that still? Because I will shout, I will get excited, and I'll start shouting, and then everyone will go deaf. Right, okay, so this room is actually double booked in our program, so if you're here for a talk on cloud-based detection and botnets, then this is the right room to be in. If, in fact, you're here for extended security on Xcode, then you need to be across the room in lab 002. So this is your last chance to escape. Otherwise, we're going to talk about malware detection in the cloud. So your last chance. Thanks for coming. Right, okay, let's get started. Okay, so welcome everybody. Welcome to the conference. My name is Mark Graham, and as I said to you a few times now, I am going to be talking to you about cloud-based detection techniques. We're going to be talking about some techniques that we all know, we all use, we all love for detecting botnets and malware, and we're actually going to see why some of these techniques aren't quite as robust as we think they are. And then I'm going to end the talk with just a little bit about some of the techniques that we're studying here at Anglia Ruskin University. So, problem number one, how do we change the... help someone from AV? There we go, cool, got it. Right, okay, so as I say, my name is Mark Graham. I'm a PhD student here at Anglia Ruskin, and I'm studying the behavior of botnets and other malware in virtual environments. And part of what I'm doing is I'm actually looking at anomaly detection, traffic-based techniques for detecting malware. So we'll talk a little bit today towards the end about some of the research that we're doing here at Anglia Ruskin, not just in botnets in virtual environments, but some of the general research that we're doing here at Anglia Ruskin. Oops. Okay, so today we're going to talk about the way that malware is evolving. Malware's evolved very much from the early days, and as our programming techniques, as our networking communication techniques, malware has evolved along those techniques as well. So we're going to talk a little bit about the way malware has evolved. We're going to talk a lot about botnets, because botnets is what I'm studying. Botnets is what interests me, so you guys are going to hear a lot about botnets as well. We're going to talk about some of the weaknesses in traditional, what I call antivirus software, the signature-based malware detection that we all have on our PCs, on our firewalls, on our servers. We all use these every day, and we're going to talk about some of the weaknesses for exploiting that. And then we're going to talk a little bit about some of the alternatives, some of the signature-less detection techniques that are out there available today. When you study, academically, when you study malware, malware detection, it's split into two camps. So you have signature-based malware detection. So that's where we're getting a sample of malware, and we're analyzing that malware to come up with a kind of a fingerprint for that malware, and then we're looking inside of packets, inside of programs, memory, and packets for those signatures of that malware. So that is very much at an application level. It's very much in a packet inspection technique. And then the other side of the coin is what we've got is anomaly-based detection. So anomaly-based detection is more looking at the behavior of malware rather than looking for a specific fingerprint. So that's very much more at a traffic level as opposed to an application level. So we're talking layers 2, 3, 4, as opposed to application level, which traditional antivirus software has been very much involved in. So we'll talk about both of those today. Okay. So malware's changed over the years. I'm going to ask a question now. Hands up, anybody who knows what the first malware, the first virus was, and when it came out. Anybody?
It was developed in Pakistan, wasn't it?
What do you think it was?
What's that?
What do you know? What do you think it might have been?
I heard it on the news.
Right. Okay.
It was a set of brothers who were living in Pakistan, at least according to this station. It might have not been the reality.
Okay. Well, according to my notes, I'm not sure if they're right or not, but the first recognized malware was back in 1971. It was the creeper virus, and it was a piece of self-replicating code that attacked DEC machines. This is how long ago it was, and it was actually propagated over ARPANET, so pre-internet days. So this was a long time ago. A virus is simply a piece of self-replicating code. That's all it is. And viruses don't have to be malicious. Most of them are today, but it's just a piece of code that will replicate itself. So these first viruses very much relied on human intervention for them to propagate. So they rely on somebody infecting a PC, someone taking a floppy drive, as it was back then, and inserting that into another machine to propagate. So these viruses were very reliant on human beings to spread them. As communication and networking techniques evolved, viruses changed into the worms and the Trojans that we know today. And the difference really now is that we're using networks to propagate this malware. So things like email attachments, downloads, clicking on spurious links on the internet, those kind of things. So the way that the malware has propagated over the years has changed somewhat. And then today we have kind of a third generation of malware, which is botnets. And these botnets differ very, very differently to worms and viruses. And the botnets rely on mass attack, mass coordinated attack on a single victim. So viruses and worms and Trojans, they very much infected one machine, did what they need to do, and then moved on to the next one. Whereas botnets, they'll sit together, they'll work to become a mass of compromised machines and attack accordingly to what they're designed to do. I think the popularity today, botnets are a very, very serious problem today in IT security. And I think the popularity of botnets comes because some of these free do-it-yourself, build-it-yourself botnet kits that you can get on the internet. So Zeus botnet, Zeus malware is a very, very popular a botnet, which you can just go down, download off the internet. Even someone like I can do that. I can download the source code, create my own botnet, and away we go. So these do-it-yourself crime tools, where they're very, very accessible, you can pay for the latest version, or you can download the earlier versions, and you can create your own botnets. And that's what's driving botnets, making botnets very, very popular today. And another statistic for you before we move on, SANS did a piece of work earlier this year to look at how long it takes a brand new unboxed PC connected to the internet to get infected with a virus. Anybody want to guess how long it would take? It's a brand new PC, plugging it into the internet. How long is it going to?
5 minutes.
Who said 5 minutes? 5 minutes, exactly. 5 minutes is all it takes for a brand new PC. So that's, you've plugged it into the internet, you haven't even finished downloading your updates yet, and you on average, you are infected with some type of virus. So viruses are very much, a very, very big security problem for us today. Oops. Okay, so what this diagram shows is a very, very simple topology of a botnet. Hopefully some of you guys are familiar with botnets and know how they work. But as I said earlier, botnets differ to normal malware in the fact that with botnets you have a whole network, a whole army of compromised machines, and whereas a normal virus, a normal Trojan or worm or virus will infect a machine, do what it needs to do. That might be a keylogger or delete a file or encrypt a file. It will do what it needs to do, then it will try and propagate onto another machine. The way botnets tend to work is they might get compromised, and they might not do anything for a while. But what they're doing is they're waiting for this botnet to get bigger and bigger and bigger and build up a kind of a mass, an army of infected devices. And botnets can vary in size anywhere from a handful of botnets, and the average size botnet is somewhere around the region of a couple of 100,000 botnets. The problem is, as you become bigger and bigger and bigger botnet, the easier it is to be detected. So botnets try to limit themselves to a couple of 100,000 devices. Now, these devices are operated at the top there by a human bot master. So it could be a number of bot masters, but these guys are the ones that are controlling these botnets through one or many servers, and they're controlling what these guys are doing here. So they might be waiting for an attack, and all of a sudden they'll launch a mass attack. A couple of 100,000 botnets will do an attack of some sort on an unexpected victim. So that makes these guys very designed for specific types of attack. One of the biggest attacks that these guys are known to do, botnets are known to do, is spam and denial of service. When you think about it, you've got a whole bunch of these machines, very easy for them to send out a whole bunch of emails or broadcast a whole bunch of bandwidth hogging denial of service attack. It's estimated that somewhere in the region of 60% of internet traffic comes from botnets doing spam and denial of service. And that to me, that's a big figure, that's a hell of a lot. The other thing that botnets are very much designed to do is ID theft. So hopefully most people here in the room have heard of Zeus. Zeus was a banking Trojan, and what Zeus does is it installs a keylogger, and it sits there silently on your PC, and every time you log onto a bank or log onto the internet and Facebook or LinkedIn, whatever you want to log into, it's going to record your details and send it back to a command and control server. So it was estimated that last year, 2013, somewhere in the region of 900 different financial institutions were affected with the Zeus malware. So again, I think that's quite a scary number. And the kind of third attack profile that these guys are ideally designed for is click fraud. So you've seen on the internet where you will click on an advert and it takes you to a web page. The owners of that web page get a penny or a fraction of a pence for you clicking on that link. If you can get a whole bunch of these botnets just constantly clicking on these links all day, you're going to earn yourself some money. And then an average size botnet, maybe 100,000 bots in a botnet, will earn somewhere in the region of $1 million a month on click fraud. So again, that's quite a scary number. The advertising industry reckons that somewhere, depending on what reports you read, somewhere between $100 and $400 million a year is being lost to botnets through click fraud. So this is a serious problem here that we need to address. But don't get me wrong. Not all botnets are bad, you'll be glad to hear. Just maybe 99.9% of them are bad. And a bot is simply a robot. It's just repeating a repetitive process. That's all a bot is. So companies like Google use bots to crawlers and spiders to index the web. If you've got a lot of data to index, like SETI, for example, they use bots to search for signals of extraterrestrial life. So don't go away thinking all bots are bad. Just the huge majority of bots are bad. Not all viruses are bad. The huge majority of them are bad. So take that message away. Come on. Okay, so traditional antivirus software, as I alluded to a little bit at the beginning, relies on us getting a sample of that malware. That could be through something like a honeypot. It could be through someone getting a compromised file and sending it to an anti-malware researcher. But first of all, we need a sample of that malware in order to reverse engineer it. Now, very often that malware is encrypted, so we need to decrypt that somehow. We then reverse engineer the code, and we're looking for certain signatures in that code to go away and create a fingerprint of that specific malware. We then upload those fingerprints to antivirus software, and you're protected. Now, the problem with that is the time between releasing malware into the wild and actually creating that sample and uploading it to your antivirus software could take anywhere between a couple of days. Sometimes it takes weeks, sometimes it takes months. So there is a period, there's a window where your antivirus software is not protecting you because we haven't got a sample of that virus. We're relying on a signature fingerprint of that virus to detect it, and we haven't got that virus. So one of the biggest issues with signature-based detection is that period where it's not where we haven't got the sample to be able to detect it. Now, it's a lot easier for malware authors to change the code than it is for these guys to go for researchers to collect the sample and create a signature. So it might take a malware author a couple of seconds to change its code, the binary of the botnet, enough that the actual attack vector hasn't changed. It's still doing exactly the same attack, but the binary has changed enough that the signature-based detector doesn't recognize it anymore. And so one of the simplest techniques that the malware author can use is they can change their compiler settings, recompile exactly the same code, and they've got a big enough change in the binary that signature is no longer recognizable, and we need a new binary, a new signature of that new variant to detect it. So some of the other techniques that they can use is they can use noise at the beginning or the end of the binary to change the profile, or they can just insert some pointless code. So we could put A equals A. It's a piece of null code. It doesn't mean anything, but that is enough to change the definition of the virus enough that the antivirus detector won't pick that up anymore, and we need to create a new sample. So one of the other problems that we've got with signature-based detection is it cannot cope with malware variants. It struggles with the, making a slight change in code. We need a new signature in order to detect that. So we use what's called heuristic detection. Now, heuristic detection is really a less exact way of detecting malware. We're rather than looking for a specific fingerprint, we're looking for similar traits amongst malware. So I was trying to think of an analogy. So rather than looking for a fingerprint, we might say that all malware has 4 fingers. Anything with 4 fingers is bad, therefore we treat that as a malware. And now obviously that's not true. Anything with 4 fingers might be good, it might be bad. So the problem with heuristics is we get a lot of false positives. So whilst we're picking up detecting malware that doesn't need an exact signature, we're getting a lot of false positives. And heuristics also takes a lot of processing time, a lot of power to perform. So we often see nowadays that anti-malware, antivirus software will do a signature-based scan, and it will also do a heuristic scan as well to pick up what it didn't detect the first time around. And another issue that we have with antivirus software is that nowadays it has to scan so many different types of file that file parsing exploits are a real problem. So an example might be that we've got a piece of malware that is easily detectable by its signature, but if it presents itself as a different format to antivirus software, it will bypass the antivirus software. So it might be an executable file, but it's saying to the antivirus software, actually, no, I'm a JPEG. The software is going to look at different places for different signatures, and it's going to bypass our virus scanners. So these are some real problems that we've got today with signature-based detection. And for those of you at the back that can't actually read this, what I've done at the top, that is actually a quote. Traditional antivirus software is dead. That was said by a guy called Brian Dye. Now, for those of you who don't know who Brian Dye is the VP for Symantec. He's saying that antivirus software is dead. Now, hopefully you all know who Symantec are. They're one of the biggest antivirus software companies out there. For him to turn around and say that traditional antivirus software detection is dead, it means a pretty big thing. So he estimates that we're probably, through signature-based antivirus detection, we're probably picking up somewhere in the region of 40 to 50% of the malware that's out there. So that means we've still got 50 or 60% of the malware that we're not detecting with these techniques. So, yes, don't get me wrong, I'm not giving you the message to go out and uninstall your antivirus software. Please keep your antivirus software on your laptops, on your servers. Don't stop using it. Signature-based antivirus detection is very good where we know the malware, where we've got a copy of that malware. It will detect it, it will pick it up, it will disinfect your machine. It's just not very good for the stuff that we don't know about. So, okay, so before we talk about other techniques for detecting malware, let's talk a little bit about how botnets in particular have evolved over the years. So this diagram here is showing its time along the bottom, and it's of different types of botnets that have come along as time progressed. So back in the early 90s, we started to see the first botnets coming out, and these botnets were based on IRC, Internet Relay Chat. And they would talk to each other using this protocol, and very easy to block. We'd simply block port 6667, I think it is, for IRC, and once you block that malware is not going to get onto your network. So malware authors cottoned onto this and said, well, tell you what, rather than use IRC, let's use a protocol that's a lot more difficult to block. So they use HTTP, and you can block port 80, but it's going to cause your users, people using the internet, it's going to cause them a lot of disruption. So we saw botnets move from IRC to HTTP-based malware. Botnets have also changed as networking technologies has changed as well. So the first botnets were very much centralized botnets, command and control server botnets, client server botnets. So if you remember the picture we saw earlier, we saw a bunch of botnets, a whole bunch of botnets being controlled by 1 or 2 servers. Now, the problem with that is because you've only got 1 or 2 servers, you've got a single point of failure. So to take down a botnet, what you want to do is you're going to go for those servers as opposed to disinfecting individual machines. So you take down a server, you're going to take down a botnet. So that we started to see multiple servers and viruses, malware, botnets dual homed, so we take down one server, the botnet wouldn't disappear, they would simply rehome themselves to another server. The problem with that is you need to start the networking skills and the programming skills to do that. The more and more servers you get, the more and more complicated it is for these to actually design and build botnets. So in the beginning of this century, we saw botnets move from command and control client-server-based topology to decentralized. So this is peer-to-peer technology, peer-to-peer topology, where every node within a virus could be either a client or a server. So all of a sudden you've got botnets out there that are a lot more difficult to take down. The flip side of that is they're a lot more easier to infiltrate. With a peer-to-peer botnet, all you need to do is actually become part of that botnet yourself. If you can get your PC to become part of that botnet, you can then start to track some of the communication traffic between that. So whilst decentralized botnets were the next evolution and they were harder to detect, they were actually they were a lot easier to actually become part of that network. And then so just recently, we've seen a malware starting to take the best or the worst, depending on which way you look at it, the best parts of centralized and the best parts of decentralized to come up with more of a hybrid of both. So these are now becoming a lot more harder to detect and a lot more harder to infiltrate. And we've seen just within the last year, Zeus, which is one of the biggest malware, the biggest botnets out there, they actually gave their code to their nearest competitor, SpyEye, and said, we've had enough of this market now, here's our code, go away and create a super bot using our technology. So we're starting to see botnets come out now which have got hybrid techniques and using botnets are starting to come together to form massive botnets. Now, a big misconception is that command and control botnets no longer exist. They're all distributed. They're all peer-to-peer. This is a slightly old diagram, but if we were to extend this curve up to date, we would still see very much so that centralized botnets are still very much out there. They're very much alive and well. And if we were to go onto a web page like zeustracker.abuse.ch or SpyEye tracker, you'll see that we're actually finding 1, 2, or maybe even 3 different variants of Zeus still coming out on a daily basis. So these viruses, centralized viruses, command and control based viruses, are still very, very much an attack vector that's being used today. Oh, no, we don't know one. Okay. So in order to detect botnets, we need a different technique than we've used traditional signature-based antivirus detection. So if you've got a botnet of a couple of 100,000 bots, and we've got antivirus software that's going to pick up one machine and disinfect one machine, we've still got a lot of bots out there in this botnet. So antivirus software isn't really a way of protect. It will protect an individual against a bot, but doesn't work towards a botnet takedown. So what we need to do with botnets is, as I said earlier, we need to actually try and find the command and control center, so command and control server, and by taking that down, we'll then destroy the botnet. So one of the weaknesses of bots is that they all talk to each other. They all talk to each other, they all talk back to the command and control center. So that might be for things like patches to keep them undetectable. It might be for Botmaster might be sending out a new script. They might be talking back to command and control center to say, I've found a whole load of logins here, here's my latest data I'm going to upload. Or it might be the actual attack commands that the Botmaster is saying, right now we've hit a critical mass of bots, we'll all go out there and attack. So there's this constant chatter between, there's a regular chatter between bots and the command and control center. And this is what we're using now to actually detect the presence of botnets. Now, botnets are generally on the internet. They use HTTP to communicate. So that means that to communicate to their command and control server, they need to know the IP address of that server. So early botnets used to have that IP address built in. Very simple, we get a copy of the sample of the malware, reverse engineer it, we've got the IP address of the server, we take the server down from that. So modern botnets have started to look at different ways of hiding the IP address so that we can't find them. So there's companies out there that use DNS-based techniques. Because we're going from IP addresses to domain names to IP addresses, we can use DNS record analysis to actually track these botnets. And there's companies out there like FireEye, like Dembala, that are analyzing DNS records for botnet communication in the cloud. They're then working with local authorities, government authorities or ISPs to detect the botnet and then actually take down that botnet server with help from police, from ISPs, that kind of thing. So the way that we do this is by analysing DNS records, DNS record analysis. And if you look at how botnet communication differs to human communication on the internet, there's quite distinct patterns. So if I'm a user on the internet as just me as a single node on the internet, I might connect out to google.com or bbc.co.uk or various other websites. You've got me as a single node with a few different spokes coming out. If you look at how a botnet communicates over the internet, you'll have the botnet itself will only talk back to maybe one or maybe two servers. So you've got a single node with only a couple of spokes coming out. You follow these spokes back to the server itself, then you'll see a server with a couple of 100,000 spokes coming out of it. So it's very, very different traffic profile between a human user and a botnet. So it's these different, it's not as simple as that, but it's these kind of patterns that we're looking for in detecting botnets. So botnets, the way that these companies do it is very much a big data approach where we're collecting thousands and hundreds of thousands of DNS records, looking at these DNS records and using machine learning techniques to start to look for some of these patterns, some of these signatures of bots communicating with the command and control server. So really what I'm trying to say here is we've gone from your software-based protection on a single PC, we're now moving into cloud-based techniques, looking at using the internet as a way to detect malware. So it's a very, very different approach. So as we're developing new ways to detect the malware, the bad guys out there are as quick as we're inventing a way to detect them, they're inventing ways to evade this, the way we're detecting them. So one of the ways to evade DNS record analysis is through fluxing. Now fluxing basically means to change. It means nothing more than to change. But the idea of fluxing is we're trying to, where we're using an IP address to identify the server, by fluxing we're trying to disassociate the domain name with the IP address. And there's two main techniques that we use to do that. We use IP fluxing and we use domain fluxing. So IP fluxing is where we might have a couple of thousand different IP addresses pointing back to one domain server, and the bot is rapidly cycling through those IP addresses so that we can't use DNS record analysis to actually work out which IP address is the legitimate IP address talking back to the domain name. And because we're cycling through those very rapidly, that's known as fast fluxing. The opposite of IP fluxing is domain fluxing. So here we've got a few thousand domain names that we're cycling through, going back to one IP address of a command and control server. And domain fluxing is generally the technique that's used today. Now, again, in the early days, the malware authors would put the different domain names, they'd put maybe a couple of hundred domain names actually into the code of the malware. We'd get the malware, we'd reverse engineer the malware, we'd come up with those domain names. So they needed new techniques in order to be able to do domain fluxing and create new domain names. So they use a technique called domain generation algorithm, or GGA. Now, I don't know if any of you guys, I'm sure a lot of you get spam email. I don't know if you've ever looked at the domain name on a spam email from a DGA, from an algorithm that's generated the domain name. Is very, very different to a human generated domain name. So we might use something like bbc.co.uk, whereas a DGA would generate something like $L9 small f T exclamation mark blah 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 blah. So we're coming up with something with a very, very different entropy that's being generated by these algorithms compared to what's being generated by humans. So a very good telltale sign that we've got something suspicious going on is that the domain's got a very high entropy. It looks very, very different to a normal domain. But from a malware's point of view, DGA is perfect for them because it's very difficult to blacklist algorithmically generated domain names. Because there's so many of them and because they're so wide and varied, you can't just blacklist this and say, this is a domain I don't want you to go and talk to. There's so many of them. And the other thing is because the malware is generating hundreds of thousands of these in one go, there's probably only one command and control center set behind a whole bunch of domain names. So we don't actually know which is the real domain name to go back and trace the command and control center. So DGAs and domain fluxing tends to be the main attack vector nowadays for malware, for botnets to avoid DNS evasion. And you may have heard of Conficker, Torpig, Kraken. They're all very big botnets that have been around for the last few years. These guys all use DGA techniques to evade DNS detection. So the takeaway here really is, yes, there are ways that we can detect, different ways that we can detect botnets through traffic-based techniques, but just as we're inventing ways to detect them, the guys out there are inventing ways to evade these techniques as well. So some of the work that we're doing here at Angular Ruskin is to look at alternative ways for detecting bots. And I don't know how many of you guys have ever used Flow protocol before? Anyone know what Flow? Yeah, a few of you. Okay, doesn't surprise me that the majority of you guys haven't. Flow's a relatively new-ish protocol. It's been around for a while, but it's only really been used just recently for botnet detection. Flow is defined there by in this paper here by Drago. Flow is a unidirectional stream of packets that pass through a network element. I'd actually argue that it's a bidirectional stream because you've actually got communication going in both ways. But effectively, Flow is a stream of packets that's passing through a network element. So it's a protocol for collecting and monitoring network traffic, and that's really what it's used for. So many years ago, we used to have SNMP, and Flow really has evolved from SNMP. SNMP is a polling device, so you're polling a MIB every X number of minutes, and that device is reporting back to you whether there's been a change or not. Now, the problem with SNMP is that there's a lot of overheads involved with SNMP, so it's not really an ideal protocol for using for botnet detection. So SNMP evolved into what we know and love now as syslog. Syslog is more of a push technology. It's pushing the information it's collected out to a syslog agent, and the problem with syslog is it's very unstructured. It's very good for logging, but it's not very good for reporting. So the clever guys at Cisco took SNMP, they took syslog, and they came up with NetFlow. And NetFlow is a very, very structured protocol. Because it's structured, it's ideal for reporting, and it's also ideal for looking for anomalies in network behavior. So I'm sure a lot of you have used Wireshark, and you use Wireshark to look at packets, metadata, IP address, source destination address, protocol, that kind of thing. That's what we use in NetFlow. NetFlow really is collecting the metadata of a stream between different devices and basically reporting back on everything that it's finding. Now, even though NetFlow was developed many years ago, I say it's probably only within the last 5 years that we've been using this type of technology to detect botnets. NetFlow is just one version of the Flow protocol. NetFlow version 9 was standardized to become called IPFix, and it's standardized under RFC 7001. So most devices nowadays, most network devices will have a Flow exporter of some shape or form inbuilt into them, but just because we're standardized on IPFix, it doesn't necessarily mean that that's the variant of Flow that they're going to use. So we have NetFlow, we have IPFix, and we also have a protocol called SFlow, which the purists amongst us might say that's not really a true Flow protocol, that's more of a sampling protocol. The way that SFlow, or the way that NetFlow and IPFix work is they will gather everything that passes through the devices. The way that SFlow works as a sampling protocol is it will only collect maybe every 5th packet, or it might be set to choose randomly capture packets as it goes through an agent. The problem with that is we might miss that one important packet that we needed to detect the botnet. So, NetFlow, IPFix, SFlow, they're all different variants of a protocol, and it's still very early days. We don't know which one is the best one to detect botnets. We know that NetFlow works. We still need to look at IPFix and look at SFlow to see whether they're going to work as well. So, as I said, we're using things like, to actually detect the botnets themselves, we're using things like IP source address, IP destination address, the protocol itself, the port numbers, and similarly with DNS traffic, we're building up a topology of who's talking to what, and then we're using machine algorithms to try and work out is this a legitimate network traffic? Is it botnet traffic? Is it malicious traffic? So we're using similar techniques. This is a traffic-based detection technique, so it's very, very similar to DNS. And some of the more important academic work nowadays is actually trying to work out what is in this masses and masses of data that we're collecting. If flow has a drawback, the drawback is it collects too much data. It's collecting data for every single conversation on the network. So if you've got two PCs, 192.168.10.1 talking to 10.2, it's going to capture a stream going both ways, so two streams for every single protocol. If you're running a Windows network, then you're going to start capturing quite a few protocols. So if you're going to upscale this to many, many thousands of machines, you're going to have tens, hundreds of thousands of flow streams that you need to capture and then need to analyze. So some of the clever work is being done in the correlation or clustering of what look like might be botnet signatures and actually trying to take away some of that noise of what isn't botnet signatures. So there's some important pieces of work such as a paper called Bot Cloud, a paper called Bot Hunter, a paper called Disclosure, a paper called Fresco, and all these papers are saying, yes, flow techniques are a very good way to detect botnets, but what about all this noise we've got? What are the correlation techniques that we need to use to get rid of some of this noise and actually come up with some real signals of botnets? So correlation techniques tend to be split into two different types of technique. You have vertical correlation, which is looking more for bot-related activity, domain names, outbound scans, that kind of thing. Then you have horizontal correlation, which is more looking at network events and saying, is this network event anomalous? Could it be caused by a botnet? Now, it's because horizontal correlation is looking at network events, it's not such a good way for detecting botnets. Actually, what we want to do is use vertical correlation methods to actually see real botnet traffic, real botnet events going on. So this is where a lot of the exciting cutting-edge work is being done into developing different correlation techniques. And some of the algorithms that are being used are similar to things like Google's PageRank, where Google will suggest a page for you on the internet depending on the number of clicks that other people have gone to. PageRank algorithms are being used to try and determine what of this traffic should we actually look at, what do we think is botnet traffic and what isn't botnet traffic. Okay, so So this is some of the work that I'm involved in here at Anglia Ruskin. I'm looking specifically at trying to use flow types protocol to detect botnets in a specific environment. I'm looking at detecting these guys in virtual environments. And why virtual environments? Well, there's a whole bunch of reasons. Virtual environments are the ideal breeding ground for botnets. If I can take a virtual machine, infect that machine, and then clone it again and again and again and again and again, very simply, very quickly, very easily, I've got a reasonable sized botnet in a few minutes. So not only are they the ideal breeding ground for botnets, but virtualization now is an established technology in computer networking. I'm sure most of you guys out here are well aware of virtualized technologies. Most businesses, most corporate organizations will have a virtualized network of some sort. Cloud providers will also provide their services based on virtualized technology. So virtualization really, for me, is probably the building block of the next generation of the internet. The Internet of Things, smart cities, that kind of thing, all these will have some sort of virtualization involved in them somewhere. And there's not a lot of work being done in detecting botnets in virtualization. We focus our efforts on detecting them on networks, on individual machines, or in the cloud, but not a lot of work has been done on detecting them in virtual environments. And so this is one of the areas that we're looking at here in Anglia Ruskin. I think that one of the reasons that we sort of ignored the virtual environment for botnets is there's been a misconception that botnets are virtual aware. They're aware of virtual environments. And because a malware researcher will put a botnet into a virtual machine to study it and dissect it, there's a misconception that maybe as much as 80 or 90% of botnets know they're in a VM, therefore they'll either change their behavior to act like a normal piece of software, or they might delete themselves so the researcher can't study them. So there's a piece of work done a couple of years ago by two guys called Lau and Svaja back in 2010 that actually took most of a big sample of malware to try and find out which of this malware was VM aware. Now, our preconceptions were in the high 80s, maybe low 90s malware. They actually found that only 2% of malware was actually VM aware. It would detect itself in a malware and in a virtual environment and change its behavior. So this preconception of malware being VM aware is really a bit of it is a myth. It's a misconception. And I think to prove this, back in 2012, we saw the Crisis virus. Now, Crisis was a virus that jumped from the host operating machine. It was a botnet that jumped from the host operating machine into a virtual machine. So it was able to, the first virus to make that jump, and it actively looked for VMware-based virtual environments in order to propagate it. So this was 2 years ago. We're starting to see the first viruses now to actually physically attack virtual environments. So the fact that there's not a lot of work being done in this area, and we're starting to see, this is an unexplored attack vector for malware authors. I think over the next few years, we'll start to see more and more viruses being targeted at virtual environments. So this is the area that we've decided to focus our studies on. And just to kind of tell you what we've done so far, very briefly, we've managed to, within a virtual environment, we've managed to put Zeus into a virtual machine, and we've managed to get Zeus to clone itself across different virtual machines. We've managed to detect that using flow traffic, detect those signatures against background noise, and we've been able to trace back, using those signatures, trace back to the actual VM, which is housing the command and control server. And by taking that VM down, we've done what we've tried to do. We've now eradicated that botnet from a virtual environment. So it's still early days. There's still a lot of work to do, but it's work that's definitely starting to show some good results. And I don't know if Razvan's in the audience. I can't see Razvan. This is just part of many projects that we've got on at Anglia Ruskin, using flow techniques for botnet detection. This afternoon at 4 o'clock, my colleague Razvan is going to be doing a talk on using NetFlow and IPFix to look at VM placement and detect botnets within VM placement. So this is part of a multiple stream project that we're doing here at Anglia Ruskin University. Okay, so just to finish off, hopefully what I've managed to do today is talk you through some of the weaknesses, some of the drawbacks of signature-based antivirus techniques. As I said earlier, it is still a technique that we can use if we know the virus. Please don't go out and say, Mark said uninstall our antivirus. That is not the message Mark gave us. It is still a very much used and tested, very much a useful technique today. But there are other techniques out there. There's these traffic-based, anomaly-based, signature-less detection techniques that we can use. And hopefully we've seen that malware detection has now moved away from individual PCs, protecting individual PCs. It's now moved into becoming more reliant on ISPs and cloud-based technology to detect the malware. So I think for me that opens up quite an interesting question or interesting conversation, is whose responsibility is it to protect us against these things? Is it our own responsibility? Should we be putting antivirus software on our PCs? Or should we now be saying, well, hang on a minute, this doesn't work anymore. We now need the ISPs of this world to actually protect us against this. And I think maybe the answer is both of those. I don't know what the answer is. I'm not here to debate the ethics of that. I'm here to try and discover some tools to do that. But I think over the next few years, we'll see some interesting changes in who is actually responsible for detecting and protecting us from malware. Thank you. Anyone have any questions?
Do you have an idea of how long it takes to actually do this flow analysis? So if you've got a small set of botnets, how long do you take to detect it?
Okay, so the question was, how long, if we're doing flow analysis, how long is it going to take us to detect botnets? Because we're using, because it's a big database technique, we're actually trying to do this in real time. So it's not a kind of a post-infection scanning technique that we'll do in the background. We're looking at real-time analysis. Certainly for DNS evasion techniques, I mentioned 2 organizations, Dambala and FireEye. There's a whole bunch of them out there. These guys they're doing this in real time. This is real-time analysis of data. And this is one of the problems that we've got. Because there is so much flow data, we need to get rid of a huge majority of that and actually focus on what we need to look at. So the goal is to be doing this in real time. But the goal is also to make sure that we've got enough useful data that we can throw away the rest that we don't want, but use that data to actually detect the command and control server. I think, Dave, did you have another question? Or? Okay.
Hello? Hello? Okay, it's not really. Hi? It works? Okay. So I think you spent like most of the slide giving introduction on what is a botnet, how a botnet works, different method to detect botnet. And then you had one slide where you basically introduced what you've done. So my question is, because you suggest that there is a follow-up talk this afternoon from your colleague at 4:45.
Yeah.
So is your colleague going to describe better what you did?
Okay. So
you didn't have time basically to.
Okay. So the question is, I spent most of my talk talking about different techniques, different detection techniques, and a little bit talking what we're doing here at Angular Ruskin. That was intentional for a few reasons. One is I wanted to try and give more of an education about the different techniques for botnet detection. The other reason is I am studying this. This is my PhD focus area. I've only really been studying this for a few months now. I'm 4 3/4 months into this, still counting it in days. So this is still very, very early work for me. So it's still work that I'm very much in the learning curve and starting to do. So and the other thing is some of the other work that we're doing I haven't published yet. So I can't tell you we're doing this, this, and this. And then you guys say, oh, I've got an idea, I'll go and publish it. So there's a number of reasons why I haven't done that. So you're right. My colleague this afternoon is going to do a talk. Razvan's coming towards the end of his PhD. He's been doing this for 2.5 years now. So he's been looking at slightly different areas. I say it's more to do with VM placements as opposed to actually detecting. It's detecting malware already within VMs as we're cloning them and placing them within the network. So it's a slightly different branch of what I'm doing. So I don't know if that answers your question or not, but
Okay.
yeah, it's, for me, it's still very early days.
Just a follow-up question. So if I understood correctly, what you do like net flow correlation on data that are captured from the VM. So basically you have a VM with different VM running.
Yeah.
And then you basically capture the traffic at switch level, or I don't know where.
Okay, so that's one of the things that we're trying to answer is...
Just a question. So my question is, what is the difference between having your setup and the setup where there are no VM? Suppose you have like a machine in a network, some machines are infected, and you collect the traffic at gateway.
Okay, yeah.
What is the difference between that and the VM? So what makes special having the detection at VM level?
Okay, so I think the question is, what's the difference between doing what I'm doing in a VM and doing this on a normal network?
Yes.
Yeah, okay, so there's a paper come out early this year that has done similar to what I've done on a network. But this was on a simulated network. It was on a GNS3 network, on a sort of a Cisco LAN, if you like. There probably is, I'm going to say there's no difference to the techniques that we're using here between to try to detect it in a VM versus compared to a network. But I think the issues that we've got is, or the questions that we've got is, where do we site these samplers? We could site them on a VM itself. We could put it on the switch. We could put it on a virtual router. We could put it on maybe on the hypervisor. There's a whole different bunch of areas where we could site our network flow probes, and we don't know where the best place to plant these is yet. So there's a little bit of work needs to be done to determine where the best place is. And I think when we're looking at malware in a virtual environment, it has another advantage in that malware in a VE can hide itself, like rootkits do, they can hide itself underneath the operating system. So the operating system will hide itself in the kernel so that the applications aren't seeing the malware signature to detect them. So what we're looking at is, is it best placed to have a detection system within a virtual machine, or should it be actually outside of the virtual machine within the virtual environment? So I think we're looking at using the same techniques to answer slightly different problems. So to answer your question, what is the difference between doing this and doing this on a normal network? There probably isn't. We're using the same flow technology, we're looking at the same flow protocols, the same flow parameters, so it's a very, very similar technique, but I think we're trying to address slightly different areas. Does that answer your question? Yeah? How are we doing for time? Have we got? Yeah? Okay, so I think we've got time for one more question. Yeah.
Hi.
I'm around for a few days, so yeah, I'm here for 2 days, guys, so please do come and talk to me. I'm very interested to talk to you guys about the work I'm doing.
Thanks for the presentation,
Thank
really
you.
great. Just wondering, with the large amount of net flow data you're collecting for vertical correlation, have you explored the possibilities of using some cloud services like Amazon's Redshift for computing and analysis of this data?
Yeah, absolutely. So the question is, we're collecting a whole load of flow data. Can we outsource some of this to some of these sort of big data-based analysis companies that can do some of this analysis for us? There are a lot of these companies out there. And I think, personally, I'm too early in my research to actually decide that I need to do that. But I think it is something that we need to consider, because we've got so much information. There are organizations out there that specialize in doing this, searching through big data quantities of information and machine learning techniques. And I think that's as I tried to say, flow has almost been established now as, yes, it is a tool we can use. What we haven't been able to do is come up with the right algorithms. I mean, there's so many different papers. There's maybe 20, 30, 40 different papers out there that talk about the different correlation, different clustering algorithms. And I think that is an area that still needs a lot of work to be done. And like you say, maybe outsourcing some of this to rather than using one PC, to shift it out to the cloud where there's a load of processing power to do this. Yeah, absolutely. I think it's definitely an opportunity. Yeah. Okay, is that? Yeah. Okay. Thank you very much, guys. I say. Thank you.